Right. Good afternoon, everybody. We're still in the mission engineering track, getting ready for session number 3. We'll just give one more minute for folks to come in here, and then we'll begin. Okay, we'll go ahead and get started. I'm Russell Shirey. I'm your host for this track, and it's my pleasure to introduce the speaker for mission engineering session number 3, Dr. Dan DeLaurentis from Purdue University. He's also the CERC chief scientist, and he will be presenting updates on his research task ART-010, titled Managing System of Systems Complexity for Distributed Command and Control. With that, I turn it over to you, Dr. DeLaurentis.
Thank you, Russ, and good to speak with everyone again. As you can see here from our title and our listing of our sponsor, this project was brought to the CERC, sponsored by the Air Force Research Laboratory, the Rome Labs folks who work on information systems, command and control, etc. And a really interesting topic, that the journey I'm going to take you on is intended to be a capsule version of the journey that we had on this project, because it very much enjoyably was a sort of a unique journey through this topic of thinking about complexity and how we might leverage notions of complexity to help us and help others design or redesign and operate future distributed command and control systems within the Air Force and the DoD writ large. So part and parcel, and really the thing that made the journey such an enjoyable one for me is by the fact of having these co-investigators and co-journey members, if you will. Dr. Ali Raz here at Purdue, although shortly, starting in January, will be embarking on his faculty career at George Mason University. So if you don't know Ali, keep an eye on him, keep an eye out for him and the great work he's already done and will continue to do, I'm sure, for the systems engineering and related disciplines. And Dr. Jeff Hudak, who was our sponsor, yes, through his organization, at AFRL Rome Labs. You can see Jeff is the research lead for distributed command and control, but he truly was a co-investigator. His fingerprints are all over our study report as much, if not more, than Ali, myself, or even our graduate students. So it really was a tremendous journey because of Jeff's active participation and continuous focus on helping us think as broadly as possible, which again is in my experience quite rare in a sponsor. And so really Jeff helped us achieve the progress we did because of that openness and that collaboration. I mentioned our 2 graduate students listed here. It's always important, as we heard once again in the panel session earlier, that the future workforce is something we, in academia especially, have a special responsibility to foster and encourage. And these 2 graduate students did a fabulous job and poured through a lot of literature to all of our benefit as part of this project. And now I'm happy to report they successfully did their MS thesis here at Purdue, and one is now with Aerospace Corporation and the other is with the Navy Warfare Center Crane. complexity in system of systems and C2 in the same title is fraught with dramatically wide scope, right? And so, as you'll hear in this presentation, that was definitely an initial struggle. The AFRL sponsor knew there was a greater understanding they wanted at the confluence of these three concepts. But we spent quite a bit of time at the beginning of the project defining and redefining our scope and our specific objectives. But I think the effort was well worth it. But again, the motivating notion is captured by this figure here, this cartoon. And some of this sort of thinking has been elaborated in some of our publications, one of which is shown here with one of my former PhD students. But obviously, I think we could all agree that we would love to have a simple representation of complexity versus performance and allow us to intelligently select designs or craft design alternatives that get us the sweet spot, right? We don't want the Rube Goldberg solution indicated by the red diagram or the red dots that may be inordinately complex for a given performance spec or even a little bit above. Likewise, we can't underperform on the performance spec, etc. What was really interesting that we started to discover as we frankly started at the easy part, which is, well, you know, there's been about 1.7 million complexity metrics defined out there in the literature. Let's just start going through and measuring, and then we'll measure against performance of the C2 systems. And what we discovered is, you know, there's just so many metrics, and there's so many and so few ways actually that people agree upon as ways to measure performance for C2 systems. It was an interesting confluence of kind of too many that you didn't know which were the right complexity metrics, and perhaps too few on the C2 performance. So the study research questions that sort of were in the contract, if you will, on the right-hand side, we really realized that we could make the greatest impact in this sort of one-year study by really digging into what would be the dimensions or the lenses that define complexity in a C2 context. And that in and of itself would be useful, but also a huge undertaking. So we decided to focus on that. And as we did that, though, we did want to take a look at what the literature was describing in terms of management approaches if one adopts and detects those forms of complexity. And so that's, again, I mentioned this as being a journey on this project, and but I think it really ended in a very nice place, focusing on these lenses of complexity and means that folks have talked about in terms of managing that complexity. And one final point, again, back to the diagram, we had to catch ourselves and also be careful of what we found in the literature about people assuming that the goal is to minimize complexity. I think all of us who even dabbled in this area know you don't want to minimize complexity, you don't want to maximize complexity. You want to allocate and manage complexity appropriately to get the performance benefits that come with greater complexity without or being aware of the risks. All right. You know, even that simple cartoon, if we could ever get it in just a couple dimensions, is even yet still not the whole problem, and primarily it is because it's not a static design challenge that we can just put on a 2D or even a 5D plot, and that's what it is. We know the kinds of systems we're working with, exemplified by C2 command and control systems of any variety, are dynamic, they evolve, they struggle with issues of scale, disruption, and unintended or unexpected outcomes as the system or the system of systems evolves. So we adopted kind of these three drivers, if you will, that focused our lens on management of complexity across the dimensions that I will elaborate in the presentation. And so scale, disruption, and evolution were our, again, spurs to deal with the management challenge. So that's kind of the words here, but obviously the picture on the bottom half of this slide also conveys the picture, again, sort of in the Air Force mentality, right? The continuing evolution in C2 is thinking about moving from centralized command to distributed control and decentralized execution. But again, there are so many trades to be made across each of those levels and within them, involving human and machines. There's just a lot to unpack in terms of our goal, which is helping people understand how different lenses on complexity may illuminate the challenges they face in design over time and under various disruptions, etc. So, let's see if I can. Okay, this presentation and the next 2 weeks worth of hours in the day would not be enough to cover the complexity waterfront. I think that's obvious. So we faced the challenge again in the project itself. So, you know, we started with some basic references on complexity, some of which you see here and on the next slide. But really, one way that we used to filter our literature review was to focus on those notions of complexity that had a sense of being used for design and systems engineering, and second, those views of complexity that were really trying to illuminate the broad spectrum of different types of complexity versus, again, the many papers that propose particular metrics for particular contexts. So in our study report, you just see a sample of some of the references here. We focused a lot, we found some great things from the INCOSE community and publications therein, some others, and you'll see later why some of the ones that related to both structural and temporal aspects of complexity caught our eye and were useful for us as well. Again, one particular example here from a paper from INCOSE IS last year, again, hit the mark for us in terms of offering a perspective on distinguishing traits of complexity, which, in our parlance, we kind of thought of as the lenses we were looking for. So, you can see them here on the right. Many of them would make many people's lists for things that distinguish or can distinguish a complex system. So again, as we looked at a number of references like this, we did try to look for the intersection of lenses or dimensions of complexity that seem to have uptake in a number of different settings. And this paper was also nice in that it did discuss management strategies across some of these as well. You'll see some of these words in terms of tension and balance and boundedness appearing in some of the things we included in our study. All right, so again, bringing you along on our journey as we kind of had our direction refined and we started to look at the literature, we did have to sort of anchor ourselves with a driving hypothesis that had some specificity so that we could know when we were done to some extent in the study and in the report that we produced. So again, we took the notion here is not that we dove deeply into Air Force or DoD related C2 applications, but instead just one example of a very huge trade space and design space, right? If you think about configuring the people, the humans, the comms, the functions, etc. The trade space on the right can get very big, and the number of metrics you need to evaluate trades across this is very big. So our primary hypothesis for our little local study was that there was a utility in a framework that provided and described a holistic view of the many dimensions of complexity and some relevant management approaches that would allow designers to ask the right questions as they seek to balance risk and reward in distributed C2 design or redesign, etc. So think about our outcome as our goal was to produce something that folks could read kind of over a cup of coffee on a weekend and say, this is not helping me compute, where I should put my comm systems and how big my bandwidth should be. But it really forces me to rethink that decision I made last week about, you know, how I'm going to interface with this other component, or the goal that we set for system X as it relates to a mission engineering perspective. So that was our hypothesis. And so, you know, as we start sharing our report now, we hope to see some evidence about whether other people think we can conclude this hypothesis to be validated. All right. So jumping directly to kind of the key finding in our report and in our work. And again, if you listen carefully to our panel and even to elements of Dr. Magnus's briefing this morning, beyond technical complexity, it's these other dimensions of complexity are just as important, if not more, than understanding C2 systems and actually asking the right questions, as I put it in our hypothesis, for what are the right questions to ask when doing design and architecting. So again, at the bumper sticker level, you know, it might seem like an obvious conclusion, at least those from our panel this morning. But again, what our panel also discussed is how we're all, you know, many of us are coming from the technical domain. And so even if we say the right words about our openness to other things, we may be prone to bias in forgetting about them when we actually have to do our job and do some modeling and analysis. So in particular, the dimensions that we came up with from the literature that seem to resonate with our purpose are shown here: structure, process, data, technical. It's not like technical doesn't matter. It's still here. Excuse me. People, coercive, which from the beginning caught our eye and borne out as something really important to think about as a particular lens. I'll talk about it. Organizational, and goal. And so, you know, we introduced these 8 in our report, and then elaborated on them with the management examples in the main largest chapter. But on top of this, we also found this very interesting notion of panarchy, which is kind of one potential framework for including all of these, both conceptually and potentially in some form of analysis. And so I'll talk briefly about what panarchy is if you're not familiar with it. As we learn more about it, it kind of resonates with concepts by a different name from the literature. Again, no surprise to those who've worked in the complexity field. So this was, you know, very important for us. And again, thinking about after probably a few more R&D steps, you know, the Air Force AFRL folks could really leverage these to inform their designers and operators about the more holistic picture as it relates to C2 design. All right. Again, short version, primer, panarchy. It's a concept. If you can look on the right-hand side graphic and kind of listen to me read the words here, it's a notion of this adaptive cycles within a complex system, where you have connections via multiple scales of hierarchy, where you have some independence within that scale, but interdependence among scales of hierarchy in both spatially and temporal scales. Okay, so that's kind of what you see on the right-hand side in terms of the graphic. And you may have, you know, small and fast cycles and dynamics all the way to long and slow. And on this particular graphic, we show the notions of the different hierarchies of C2 that I mentioned earlier. And so it's this notion of interaction between and among these cycles and these hierarchic levels that is of relevance. And so, you know, as we further investigate the lenses on complexity, the 8 that I mentioned, we'd like to see if we can couch them here, because inevitably, as we know, and as I mentioned on an earlier slide, scale, disruption, and evolution are going to happen, and that's going to drive these cycles. All right, so just a couple of quick examples here. If you want to think about kind of the hierarchy of a military context, where you have the warfighter component, squadron, base, and regional command, you know, those are kind of easy to start with as examples because the spatial span is fairly, I mean, one could craft different versions, but you can think of that going from a very narrow region of space for the individual warfighter to a very large and diverse area for the regional command. The time scales, again, not perfectly, but to some degree correspond to short for the warfighter and longer, short and fast for the warfighter and longer and slower as you move up the chain. And so we just sort of describe some of the aspects of the adaptive cycles that would take place within these component hierarchies and how those might manifest. But another interesting part of our journey, the more we got into this, and as we started to try to map examples to the military C2 domain and the Air Force C2 domain, we realized if we were trying to open the aperture for people within the Air Force thinking about C2, distributed C2 and design, if we only used Air Force C2 examples, it might be difficult for them to overcome their current understanding and their 35 years experience to understand these larger concepts of complexity. And so we decided to take a non-military civil application that has just as much relevance to these concepts, specifically to distributed C2, but didn't have all the baggage of the details and experience that people might bring. So that's where we came up with something that, fortunately, Ali and myself and the students had some significant experience working on, the civil air traffic management. So without belaboring the point, I think it's obvious that this is a tremendously useful example of collaborative C2 across many dimensions. This is just a graphic that we sort of adapted to simplify it from an FAA description for their modernization. And so we wrote about examples from the civil air transportation for our 8 complexity types in the report. And I think, again, that helped us even overcome some of our biases and explore new literature and new examples. So speaking of that, that example I gave for sort of timescales and panarchy-inspired adaptive cycles for military domain can also be understood here. As you start from the local air traffic control, airport control component to the TRACON, to the centers, to the command center on, you have these increasing spans, spatial spans of influence and control. And you also have these time scales that go from relatively shorter to relatively longer as well. So very nice mapping, which again helped us give some good examples. All right, so with short amount of time I have left, and with apologies that there's a lot of content across each of these areas, so I'm only able to give you the bumper sticker and certainly not the deep dive. But what we've tried to do to make it as easy as possible for those of you watching this presentation is to give you kind of the definition in the upper left, some management methods we found from the literature, and some examples for air traffic management and distributed C2 on the right-hand side box. So technical complexity is one that I will spend the least amount of time on because, again, many of us at least are familiar with this. And our study was again, not claiming this was unimportant, but trying to look beyond technical complexity. So we know systems engineering, OR, systems analysis, and hundreds of other things are very useful for managing technical complexity. Process complexity. Again, one that wouldn't be a surprise to many of you, but probably not as prone to undue focus as technical, arises when we have to put together a series of interdependent actions to achieve a purpose. So this, complexity arising from processes may be embedded in some technical designs and technical complexity, but sometimes they're not, and so that may generate complexity when those processes and physical systems have to come together. There's some interesting management methods that we found. Only a couple things shown here in terms of, being able to shift your hierarchy and align systems components within a process focusing on the value you're trying to get out of that process and not really anything else that might be residual. On the air traffic management side and the distributed C2 side in the military, our collaborator, Jeff Hudak, had great examples of how the complex Byzantine sometimes processes within the Air Force are there for a reason, but present tremendous complexity to unpack. What are the key drivers in terms of how they react to scale, disruption, and evolution? And so process complexity is a really important lens to look at. Again, thinking to the designers of the next generation systems, how might they early on think about process complexity before it's too late? Coercive complexity, I mentioned this really caught our eye. This is associated with the exercise of power, which can operate to ensure some individuals or groups have the capacity to control the behaviors of others. In a moment, I'll mention people and organizational, and so there's interdependencies between our 8 categories that we just scratched the surface on. But this one was really important, and again, I think gets a lot less attention. On the air traffic management side, there was an accident that happened. I think it was in San Francisco, the Asiana air crash, maybe 10 years ago. I forgot. Where there was this interesting sort of hierarchical relationship between the pilot and the co-pilot that one could argue had sort of a form of coercive complexity involved. And clearly in military distributed C2, no matter how much you're trying to do, decentralized execution, etc., there's still this overlay of coercion in the sense of control and how people may perceive control of command, even when it's not being overtly exercised. Data complexity is probably one I don't have to spend much time on. I think it's quite clear in our modern systems, the power of data and the potential debilitating complexity from data if we don't have an ability to understand, digest, and translate into the use for a C2 system. And so, again, there's many examples in air traffic management. Obviously, we can talk about many examples of non-alignment of data across these different hierarchic levels as well as temporal scales. So this is a constant challenge in situational awareness for distributed C2 is one implication area as well.
Dan, we have about 5 minutes.
Right, excellent. Structure complexity based on the arrangement and dynamic relationships between the different system elements. So again, this is one that probably is on the radar screen of many people, and people, many researchers, including us, when we've worked on complexity, leverage network theory, system dynamics, and things that actually allow you to look at structure of relationships as well as the impact of dynamic interdependencies and feedbacks. So again, it's important in air traffic management. You can have any number of examples of how different things propagate through these interrelated networks of decision making, as well as the actual transportation of the aircraft and their passengers and cargo going through these various types of networks, and very important across the distributed C2 military domain as well. Organizational complexity, very important, and again, perhaps something we have to pay more attention to when we do mission engineering. Again, it came up in the panel as well. These complexity here is driven by the internal interactions of the parts and who can interact with who and why in the midst of a turbulent environment. So again, I think earlier the panel, but our report, found some obvious relevance of social technical systems thinking, organizational cybernetics, air traffic management. There again, how we organize our air traffic management functions and try to combine automation intelligently. Some huge challenges there, as there are in the distributed C2 environment. I'll give an example as I introduce people complexity here as well. This is the one where, so again, it's related to coercive in the sense of how individual people may overtly sort of apply their will. But in general, the different worldviews, perspectives, and assumptions of individuals through the larger impact of culture and process and organization, has a huge impact and is just often neglected in some of our more technical design activities and processes. So there's a number of methods, fortunately, that people in the soft systems or other fields have talked about. I give an example in the air traffic management that relates to people complexity, coercive, and just about almost any other. In 2014, there was an ATC-0 event at one of the largest centers, air traffic control centers over the Midwest region of the country, because a disgruntled employee set fire to the computer systems in the basement, took the whole center down. So there was both an amazing and to some extent disturbing reaction to that really activated many of these forms of complexity, especially people complexity. One example that I really love is that the individual controllers at that debilitated non-functioning center actually had enough perspective and sort of viewpoint about what their job was that they actually drove to the nearest center in adjacent states that they thought they understood best in terms of the airspace structure and said, I'm reporting for duty, because all of that traffic had to be taken by the other centers. The disadvantage is that, some of that seat of the pants reaction, while it was all helpful, overall, there was the Inspector General actually found a lack of a coordinated plan for these kind of scenarios across the FAA structure. And so again, from a design perspective, some of these potential sources of complexity, this is a management problem, right? You want to be ready to adapt to that great complexity you get by the people in your system and their ability to react appropriately. But it's a challenge at the organizational and systemic level. And finally, goal complexity. Again, different goals may be in conflict and may interact in ways that we don't think about. If anyone's done optimization, right, setting your objective function and your constraints and making sure you're not assuming away interactions between them or contention between them is a huge challenge, let alone even if you do account for them, how do you represent them accurately? So, there's a number of management methods that decompose processes and tasks and reason about the goals embedded within them that would be useful here for a designer asking the right questions. And in air traffic management, again, across that, or military C2, across, from the warfighter to the central command and from the local airport controller all the way to central command, there's lots of different goals that get exercised and often may conflict. Also, the airline business models, by the way, in the air traffic command. So as I come to a conclusion, we only scratched the surface about the obvious fact that at different levels of hierarchy, spatial or temporal, these different dimensions some may be more prominent than others. So there's a lot to research there. And more globally, the interaction between them, if you want to think of it from a heat map perspective shown on the right, is also something that's very fruitful for additional research. And so finally, my last slide before we turn it over to questions is the way ahead that we've talked about with AFRL folks. Okay, if we accept these dimensions, how do we instrument our modeling and sim design and even operating manuals, if you will, representation systems to instrument to detect these complexity types? How do we find stable intermediate forms, given we know these are going to be evolving over time and it's not just a one-time design problem? And finally, is there something there with this panarchy construct as an integrating function, potentially computational framework for incorporating all these different views of complexity? So I'll leave it on this slide and look forward to questions.
Awesome. Thanks for the chat. Very good talk, Dr. DeLaurentis. And looks like you have several questions. So we'll start with the first one from John Wade. And the question reads, it could be said that complexity is the degree of difficulty in predicting future behavior being dependent on context, behavior of interest, time frame, and accuracy, etc. In what ways do you agree or disagree with this? And how does this relate to your C2 work?
Boy, feel like I'm back at my dissertation defense. John, nice to hear from you again, John, and to get this question. Gosh, so yes, I agree that for that very difficult phrase that's embedded in the middle of your question is actually doing prediction of behavior. As I tried to illuminate, that's really was beyond the scope. Even though we kind of started there, of course, let's see what we can calculate and predict. We really wanted to instead focus on these different lenses and see how people react to them in terms of understanding their systems better, asking right questions for thought versus predicting. But logically, at some point for decision making, predictions and evaluations have to be made. And absolutely, depending on which time scale you're focused on, you may get a different answer than if you focused on a different context or a different time scale. So I'd agree with your assessment there, John.
Great. The next question is from Robert Lewis, and it asks, have you related the C2 concept to ideas in Mission Command central to the Army's new C2 concept?
I was just looking at that word in parentheses that I didn't quite understand in the question.
Yeah, I'm not sure on that one either. I have that one.
So Robert, short answer is no. We haven't looked at the Army's new C2 concept. As I said, frankly, or even too much at the Air Force's emerging concepts. But that is sort of a logical next step, is putting this study report in front of people and saying, okay, we claim this helps you ask the right questions. What do you think about that? So that's something we could do.
Excellent. Next, from Jeffrey Hudak, who's also the sponsor on this from AFRL. Are there methods for scoping complexity to the individual nodes in the system? The shift to decentralized systems raises new concerns about the line of sight individuals have to their role in the quote machine.
Yeah, this is unfair. Jeff knows all the hard questions as the co-investigator here. A number of our dimensions, as Jeff knows, the people complexity and a couple of the others did have as sort of their endpoint evaluating the implications from complexity and for complexity on individual effectors at the decentralized execution approach. And so maybe also embedded in this question is the opportunity here that I probably didn't do a good job of highlighting. I sort of kept pointing back to the designers, and I used my hands like this, thinking about a bunch of people in a room, doing abstract design. But probably something just as powerful of our initial study and the further work would be to individual people, more people at that warfighter or people in front of the scope in an air traffic management context, that gives them this notion of line of sight of how these big, complicated, complex parts of the system are impacting them and why. I think that's something for next steps.
Excellent. A lot of good questions. Next question is the 4th out of 5 from Robert again. Have you identified any fundamental differences between military and civilian context? The example that comes to mind is the reinforcing warfighting function. Example, tank versus tank, F-16 versus MiG, and the complementary warfighting functions. Example, tank versus infantry, F-16 versus intermediate bombing target. Being good at one use case often means being bad at the other, and most DoD land domain systems need to be sufficient in both. So is there any civilian system equivalence to this concept?
Well, let's see. Let me react to the first one, the first comment there about the fundamental differences between military and civil context. So, first of all, with the term fundamental, the problems are different, but I think the fundamental constructs of using complexity in these ways are completely appropriate across both domains. But in terms of differences in the manifestation, so we also looked at Walmart as an example of a big organization that, across all those 8 types has a lot of things going on. But one of the things we found just in reading about Walmart and their management of the supply chain is, to some degree, the lower amount, we perceived there was a lower amount of goal complexity in terms of, contention and tension there versus perhaps the more messy context of a battlefield, and certainly a joint battlefield context. So that's one example where I think there'd be a difference. But I think especially with the civil air transportation and the Air Force C2 ideas, maybe because they're actually kind of so structurally closely related, we did find a lot of similarities. I don't know if I have a good answer off the top of my head about the context of the land domain system example, but there probably is one.
All right, so we may get cut off during this question because we're scheduled to end within the next 30 seconds here, but I'll try and get through it. From Peters, as a matter of practice, these all sound too complicated to collect and use in real projects. What is the current practice in using any kind of complexity metrics in systems engineering?
Great question. In less than 30 seconds, I could say I don't disagree with the question or the comment. And I would distinguish the practice of systems engineering. I think you might have detected that in our panel. For those who are actually in the practitioner world, they maybe have less ability to consider some of these things we could come up with in the academic world. But nonetheless, the bridge has to be traversed. And so that's why I said one of the next steps for our study is to put this in front of people who are not research people and see where the first lanes in that bridge of relevance might be. So very good point.
All right, excellent. Well, that's all the time we have today. Thanks again, Dan, for the excellent talk. Looks like we have about a 20-minute break and then the afternoon keynote. So enjoy the break, and we'll see you back in about 20 minutes.